out on us today, right?
I know, yeah. I hate it. I've had so many problems with sickness. I've been sick, and also I had to bail on one of my other class. I hadn't been able to do it. But welcome everyone to our Introduction to Networks course. I am glad to have you here today. Like I said, I'm sorry for any classes I have missed. I know I've had some health issues. It has been a rough 2 weeks for me, but things are looking up, so we're glad about that. You'll see we should be around chapter 6 right now. I think we're fairly close. I did send out last week a link to the entire class to a set of videos that will give you lectures for all the chapters. So I'm not going to actually lecture per se on every single chapter. I do want you to go through those lectures as we're doing this. Now this is very good that this actually happened. This is something that occurs when the browser has a problem with the local cache. And so you can go in and clear the browsing. So let's go in here and I'm gonna clear everything. All right, so I'm clearing everything here. And I'm gonna do it again just because. And I'm gonna go back and close it. And you can probably see this too, but this was pretty neat. This was actually an article on how the oil and gas companies are using IoT. They're being slow to use it, but I'm gonna log back into Netacad. Oops, wrong place. And hopefully this will fix our issue I just had. If not, then the issue is I'm using Edge, and I can switch out of using Edge, but I was gonna, man, I cannot type today. Edge is not actually recommended for using inside of the Netacad. I'm using it so I can use my my touchscreen. I have a touchscreen on my desk, and I'm trying to use it so that we can I can draw some stuff for you, which is kind of neat. Especially once we get into IP addressing and I'm drawing lots of ones and zeros, I won't have to try to do it in Notepad, which is always a problem. So let's see if we can make it work this time. And launch course. Yep, so you see, I fixed that problem right there. Well, I was logged in, but when I went to go log in and actually get access to the curriculum, it told me that I wasn't, and I needed to log in again. So I went into the browser and cleared the browser cache and cookies and everything. So be aware that's one thing that can definitely happen if you're using the curriculum, and it's something that you can have as an example now for you to be able to fix. What I want to do is talk a little bit about some different things, but what I want to talk most about is this concept of encapsulation. And we're going to talk about, and the neat thing here, again, I can touch my screen. What is the name of this particular model being shown right here on the screen? Do you remember? All people seem to need data processing.
You okay?
This model was the OSI model, Open Systems Interconnection model. And we also talked about the TCP/IP model, which consisted of 3 layers, and we considered those to be the application layer. So we had the app layer here. We had a transport layer that was right here. We had an internet layer. Now, by the way, folks, I am not an artist by any stretch. Add in the fact that I don't really have good use of my hands, and I'm pretty bad. The internet layer, and then at the very bottom, I do have a new pen coming in, though, that will write better than this. We have the network access layer. And I'm also left-handed, so my handwriting is pretty horrendous regardless. I've been hit by a truck, and I have horrendous handwriting. So we've got the @in, or as someone told me, if you do it from the first layer 1 to the top layer, it's NITA, N-I-T-A. So I'm going to tell you that you need to know these 2 different types of models, the TCP/IP model and the OSI model. All right. You also need to know the different layers. So all people seem to need data processing, which is layer 1 or layer 7 to layer 1, or please do not throw sausage pizza away, which is layer 1 to layer 7. So this is layer 7, this is layer 1 down here. When we start talking about these, we talk about how Ethernet is a type of layer 2 protocol. So we're looking at Ethernet down here at layer 2 and layer 1, but it's really a layer 2 standard where we're looking at how we're going to do framing. We did talk about, in our last lecture, we talked about protocol data units, or PDUs. That's harder to do than you think. PDUs, and we talked about how at layer 1 we call them bits. Layer 2 is frames. I might have to lean this monitor down so I can do better. Bits, frames, datagrams, or packets at layer 3. I've definitely got to get a better pen. Packets and segments. I know class is going to be like, I wish you had never learned that you could actually write on this screen. But bits, frames, packets, or datagrams. Sometimes these are called datagrams. In some of the documentation you'll read, you'll see datagrams. All right. So these models are important because it allows us to talk about things. So if I say something's layer 2, we know it's dealing with logical link control, and so that's how the layers talk to the upper layers, and it's talking about media access control, or how you put things onto the wire. Very important. I'm going to discard these. Move forward. And you'll see the MAC sublayer, we talk about how it is this logical link control that provides basically the connection or the ability to interact with the upper layers. I'm going to go back just a second and show you something. We've talked about two different types of network layer protocols. We talked about IPv4 and IPv6. Okay, so when we look at IP version 4, that's our predominant type of IP. But at layer 3, we also can have IPv6. Here's where the makers of TCP/IP were brilliant. What they said was they really didn't define anything at the data link layer or the physical layer as a protocol. And with the LLC can be rewritten so that it can talk to either IPv4 or IPv6 without changing drastically anything to do with the upper layer protocol. And so that's the key to Ethernet being so predominant in the networking world today. It can be used with IPv4, IPv6. It could be used with different protocols if different protocols were developed. It can also be changed to handle different methods of media access control. So we can use 802.3, which is typical standard, Ethernet in speeds from 10 megabits per second up to 100 gigabits per second. In fact, we just got in switches for our data center. We're going to have 100 gigabit connections from our core spine out to our leafs, and then we will have that connectivity out to them, and then we'll have 40 gig back to our backbone on the campus. So it's going to be really interesting what we can do. But you can see there are different standards. So 802.3 is standard Ethernet. Then we've got 802.3U, which was fast Ethernet. That's 100 megabits per second. We've got 802.3Z, which is gigabit. And then you've got the other standards moving on up to the other speeds. You've also got wireless. You've got all these different things. But we don't have to rewrite the entire protocol because we've got this logical link control that allows us to do all of these different physical layer standards that can use the same media access control and then talk through the logical link control. Now, in this day and age, you're not going to see very many 10 base 5s or 10 base 2s. This is old thin and thick net Ethernet over copper. We talked a little bit about copper cabling that was using BNC connectors and those type. So coax BNC, coax N style, you're not going to see much of that. Maybe you could possibly see it in an industrial environment. You're not going to see it much in normal networks. You will, though, see 100 base TX and 1,000 base T. You're going to be more often see 1,000 base T now than even 100 base. So what does Ethernet do for you? It gives you a frame, and it gives you the ability to, and this is Ethernet too, but it's how devices on the network can see information coming across in the bits. So there's an 8-byte preamble. There's 6 bytes for the destination address, and you're going to learn that is the MAC address. And there's 6 bytes for the source. There's a type that tells you what it needs to be sent up to at the upper layers. And then there's the data, which is carrying all that encapsulated information from your upper layers. And then an FCS, or a frame check sequence, that is a mathematical equation that's run against the frame and then run again when it's sent and put on the end, and then check again on the receiving end to make sure the frame has not been changed and therefore damaged in transit. So as we're going through here, you see the different frames again, and again, ether type tells you whether it's going up, and common values are 0800, which is IPv4, 086DD, which is IPv6, and 0806 for ARP. You don't need to remember those, but it's nice to know them if you're doing in-depth packet analysis. This is kind of cool. One thing I hope you know, the curriculum does have the ability to do drag and drops, which is really neat for your students. And again, these are not the correct answers, but that way you can check and see that it's incorrect. But it's kind of neat that you can do drag and drops for your students. And they usually have a couple different ones. So you want to do 8023 start frame delimiter, and then on so on and so forth. So incorrect. Okay. Be the preamble and then start frame delimiter. All right, you had a lab, or you do have a lab that will let you go through and look at these items. And we're going to talk about MAC addresses. Now, the reason they show you hex is because MAC addresses are in hexadecimal. So we see that MAC addresses are going to be 48 bits, but they're being expressed as 4 hexadecimal digits. Hexadecimal is base 16, which means it uses 0 to 9 and A through F. And A through F represent 10 through 15. 0 is considered a number, so you've got A through F. A MAC address is the structure used at layer 2 in Ethernet to determine the address of a device. It's made up of 2 different sections. One is the OUI, the Organizational Unique Identifier, and that is typically, well, it's not just typically, that's set by the IEEE, and it will be the same for all vendors. So if you get anything from Cisco, it's going to have something 00602F if that's a Cisco OUI. You also can actually go out and do OUI.
Jesus, I got an earful.
OUI vendor lookup. You can actually go in and do MAC address and OUI lookup. I'm going to. Sharon, if you will you mute yourself? Actually, I will. I got you. And then if you need anything, just type in the chat and I'll unmute you. Would that be good?
That works.
Okay. So you'll see here that you can actually do a MAC lookup or an OUI lookup. So I'm going to give you one here. I'm going to go and pull up one on my PC. I'm not going to show it to the world, but I'm going to put in the first portion of my Ethernet. I got to do /all, forgot /all. And so on my Ethernet adapter, my OUI is D8-9E-F3. Actually, I am going to unmute you, Sharon, because you can't really ask questions if you don't. There. All right, so let's look it up. And you'll see this is by Dell. So if you were looking at a frame and you had this as the first portion of the MAC address, you would know that came from a Dell computer. Which, by the way, this is how they call it the BTK killer. He sent a manifesto into a newsroom or into a local news organization in a Word document. That Word document stored the MAC address of the PC used in the creation of it. They went in, found the computer it was from, tracked it, went to Dell. Dell was able to find the serial number and then find who that was sold to, and then the police could go and capture that person. So that's one way that OUI could be used. It could also be used if a device on your network was spewing out a large amount of traffic. You could go and find that device. But that is a MAC address, and it's very important, especially in Ethernet. because when you frame forward, the way it's in traditional Ethernet, this is how it works. You need to send information to H3. You're going to send out to the destination MAC address, source MAC address, everything goes out, and it goes to everybody unless the switch knows it. And everybody will look at it and say, well, that's not my address. Okay, I shall ignore it. Don't know why they suddenly went to Old English. But this one says, this is mine, and starts, we'll actually pull it down and look at it. You'll learn that switches will actually learn and filter MAC addresses. And you see here, ipconfig/all will give you the MAC address of your PC, which is pretty neat. And there's different ways to represent it with dashes, colons, or with periods, depending on how it's written and how the operating system does it. What I really want to do with this is talk about the fact that when we're working with MAC addresses, hold on one second, folks, sorry. Okay, sorry. So when you're looking at this and you're looking at how devices use MAC addresses, one of the ways is when a device needs to send something directly to another device, it can use what's called a unicast. In other words, it has a destination MAC address. The thing is that most devices don't know other devices' MAC addresses automatically. So you're going to learn about ARP, an address resolution protocol. So what's going to happen is the host, if it needs to send something to this IP address and it doesn't know the MAC address, so let's say it doesn't know, it knows this IP, but it doesn't know the MAC, it sends out an ARP request. And that ARP request is broadcast. It actually goes out to everyone, and when they see it, they'll send back an ARP reply if they are the owner of that particular IP address. So it says, who has this IP address and what is your MAC address? That's what the ARP request says. And then the ARP reply comes back and it would be, okay, I am this IP address and this is my MAC address. And then H1 can put it into its MAC address table. And then it can build the frame. That's an important concept, and that's that unicast. If you need to broadcast, you send it to the, I call it like the cat spitting MAC address, all Fs, which is actually all ones in hexadecimal. So all Fs is everyone has to look at it, and switches will actually send out to every single port except the one that came in on any broadcast. So that's why switches aren't necessarily good for stopping broadcasts. And then there's a multicast, and multicast is a special one to some, and it's based upon a special MAC address that those particular devices are listening on. So it's the big thing with it is just remember one to some. So you're going to look at the MAC addresses on different devices in our labs, and we're going to use, when we're going to talk about switches, we're going to learn how switches deal with MAC address. Now, a switch is a layer 2 device. It's important for us to talk about that. We talked about the OSI model, and we talked about how it allows us to talk about devices in a similar fashion or to understand how they work. So when I say a switch is a layer 2 device, then we know it works with framing. It works with MAC addresses in the Ethernet world. In this, however, though, they are using shortened MAC addresses just because it's easier to do. But a switch builds a MAC address table or a content addressable memory table which is this MAC address table, it is built by the switch seeing frames coming in. So when a frame comes in, the switch looks at the source MAC of that frame when it comes in a port and says, well, if that source came in port 1, well, then that MAC has to be on port 1. And when you boot a switch up, it doesn't know where anything is at all. There's no MAC address table on it, unless you statically assign MAC address tables, which you can do, but we rarely, if ever, do. So it learns by watching the frames come in, be that a frame that is destined to a destination unicast or a destination broadcast or even multicast. It's going to build that table. As it builds that table, okay, it will try to fill it out. But if it's not in that table, so let's say that we're sending something to a destination MAC address of 000D, and that comes in and it's from 0A, so the switch will put 000A into its MAC address or CAM table, but it doesn't know where 000D is. Because of that, it has to flood it out all ports except for the one it came in on. It's going to assume it's not on the port it came in on because due to traditional Ethernet, it should be on this same link. If it's not, it should be on this bus link or this link here, and should be able to see it if it's on this link. So you wouldn't have to send it back out the one it came in on. What'll happen is if D responds, well then the switch will put D's MAC address into the CAM table for port 4, and at that point it will know where A and it will know where D is at. It still will not know where B and C is at. The beauty then is if MAC of A sends something directly to D, it will send it directly. The switch will send it directly from port 1 to port 4, actually to switch it from port 1 to port 4 or port 4 to port 1. 2 and 3 will not have to see it. And even better is the fact that when 2 and 3, if they were talking to each other, 2 and 3 could be talking to one another at the same time that 1 and 4 are talking to one another. So that way you can do what's called micro segmentation, and that is when a single port has on it a single device and the switch understands that and is able to filter without having to, without unnecessary traffic going to ports. Does that make sense?
It does.
Okay. So again, switch is a layer 2 device because it deals with frames, and frames are the layer 2 protocol data unit. So that's important. Now, one of the things that's a little different though is what if a device is not local? If a device is local, I can send out an ARP request and that device will then send me back the ARP reply. But if the device is on the other side of a router, it's impossible for that device on the opposite end to send back its MAC address because routers will not pass the ARP request broadcast. What actually happens in that case is the router will return its MAC address, the one for the default gateway. It will send it back as the MAC address for that remote host, and that's called proxy ARP. It's where the router proxies its MAC address for a remote host. These are really cool because they keep changing. You can do new problems, and it asks you, where will the switch forward the frame? And so you look here, 0D is sending in FA7. Destination is 0A. Okay. You look down here and say, all right, nobody knows, it doesn't know where 0A is at. So where's it going to forward it? It should forward it to all the ports that are connected. So FA1, FA3. It won't send it out FA2 because it's not up. FA4 is not up. FA5. It won't send it out FA7 because it came in on FA7. It will send it out FA9. And then when the switch forwards the frame, what statement is true? Switch adds the source MAC to the MAC address table. Let's see, look at this. No, it's already, was it there or not? FA7, it's already there, so it's not going to do that. Frame is a broadcast frame, will be forwarded to all ports. Let's see, nope, it's not a broadcast because it's being sent to 0A. So it had to be sent to FF if it was a broadcast. Frames of unicast and will be sent only to specific port only. Well, that would be true if it knew where 0A was at, but it's a unicast and will be flooded to all ports. Okay, because it didn't know where that particular port was at. So it has to flood it out all ports and find it. Once it would, the request or the reply goes back, then it would know where 0A is at. But the good news is you can just keep doing problems and changing them, checking them. It's basically being generated in the background. So your students can really use this to get a solid understanding of how switches, hey, Lena, glad you can make it, get a solid understanding of how switches use their content addressable memory table or their MAC address table to filter frames. So make use of this. This is on this 5216 activities, one of my favorites. Okay, I'm going to let you read about those. That's pretty easy stuff there. I will give you a quick warning about this auto settings. Sometimes we see speed and duplex settings. Duplex, when we look at duplex, there's really three different types. There's simplex, which is one way. There's half duplex, which is like if you've ever watched the National Geographic or used a set of walkie-talkies, base camp to camp 2 over. It's always a British dude. Half duplex is you can either send or receive. You cannot do both at the same time. So that's half duplex. Full duplex is you can send and receive at the same time. So it'd be like having a cell phone conversation. Full duplex, trying to talk to a half duplex side gives you errors because one side is expecting half duplex, one side is expecting full. Same thing with speed issues. By default, many devices like to auto negotiate these, okay? And they do it with auto negotiation. I personally like to at least set on the switch side the speed and duplex manually. So they can use the command speed 1000 or speed 100, duplex full. That's the typical commands on the switches that we use. And that sets them so that you don't have to worry about auto negotiation. Or you can set it on the switch and leave it as auto negotiation on the PC, and the PC will be told by the switch, I can only do full duplex at 1000 megabits per second, and then the PC will do that typically. You can still get an occasional issue here and there, especially if you have like a NIC and a printer, and that printer NIC is only able to do 100 megabits per second, and you set the switch to be 1000 full, and it can't do it, then for whatever, the link won't come up, and you have to kind of troubleshoot that to figure out that that particular NIC doesn't support gigabit speeds. Auto MDX, this is one of the things you've been doing inside of Packet Tracer, and that's the idea is when you connect two like devices, so when you connect a switch to a switch, you really should use a crossover cable. But in the modern world, with all Cisco releases 12.2 and higher, you pretty much can just connect a straight through cable here and it will auto MDX or auto cross for you. So you don't have to worry about that anymore. However, if you're ever asked on a question on a test or a Cisco certification exam, what's needed to connect a router to a router or a switch to a switch, use a crossover cable. The weird thing is though, when you connect a switch to a router, you actually use a straight through. You don't use a crossover because the port on the router is considered to be a network interface card. Same thing with a PC. From a switch to a PC, you use a patch cable or a straight through. So again, communicating on the local network, I can just send out a ARP request and then get an ARP reply, and then I can build my local MAC address table, which there are MAC address tables, by the way, on PCs. If you do ARP-A, you can actually see that. If it's remote, however, I send an ARP request. The router sees that, oh no, that's for a remote destination, remote IP address. So I can't forward that ARP request. I will reply with my MAC address, so the MAC address of the local gateway for that network segment. And so this becomes what's called proxy ARP. Very important concept. Very important that you understand it. So it's proxy ARP. Lena, you weren't here earlier. I'm using the drawing capabilities of my monitor I got, and so be aware. Hopefully, I will get a better pen, and it won't look quite so bad. But no guarantees, because I am left-handed and I have been hit by a truck. So there you go. But this is called proxy ARP because the router is proxying its MAC address for the destination remote MAC address. Any questions on the difference between how a local ARP request works and how a remote ARP request works? You will see this somewhere. I'm just going to put that out there. All right. Okay, so again, they're just now they go to introduce ARP to you. Here's the ARP process and ARP request. So who has the IP address of this and what's your MAC address? Whoop, that's me. I'll send back my MAC address. So exactly what I was talking about. So in the local situation, the ARP request is a broadcast. It gets forwarded to everybody. The host that has that IP answers with its MAC address. Host 1 can then build the frame and send the frame directly unicast from H1 to H4. In addition, once this has occurred, H1's MAC address should be in the CAM table of the switch, and H4's MAC address should be in the CAM table or the MAC address table of the switch. H3 and H2 would not be in it yet because they haven't communicated, assuming this switch has just been brought online. There's good video demonstrations on this that you can watch in the class here. I'm not going to sit there and do that. You can actually remove MAC address entries in a CAM table. Locally on Windows devices, it will be removed from the ARP. MAC address entries will be removed from the table if it's not used within 2 minutes. If it's used again within 2 minutes, I think it has a lifetime of around like 30 minutes. On routers, the table has a lifetime typically of around 4 hours. So a router can learn it, and same on switches. Here's an ARP table for a router, show IP ARP, and you can see the different IP addresses and the mapped MAC addresses. Likewise, on a PC, you do ARP-A, and you will see all the IP addresses on your machine and the physical addresses. Now, physical address is another name for MAC addresses. And the reason is, I didn't mention this earlier, but a MAC address is burned into the network interface card. So when you actually purchase a network interface card, it has that OUI, the organizational unique identifier, and it has the serial number. So the first 24 bits is the OUI. In fact, let's see if we can find this one. Let's go, what was it, 64? Where'd I go here? There. 640F29. 640F29. Look it up. Found 0 results, so it must be a fake one they put in there. So they must have just threw a fake one in there instead of using a real one. 0F29. Yep, 640F29. I guess they didn't want to get caught up with anybody. Let's look up vendor. Nope, 0 results. So no vendor for that one. So very well could just be something they put in there faked. If it'd been real, you would have gotten an OUI. Now the bad news is ARP broadcast could be somewhat a security problem, but not really. The biggest issue is if someone's locally able to get access to your network, they could spoof the MAC address of the default gateway. So they do a denial of service attack on the default gateway for that particular link. And then they tell everybody on that network that they are the default gateway. So when you said, I need that MAC address of 192.168.1.1, they've overloaded this interface so it can't respond. And they say, oh, that's me over here. And so they give their address or their MAC address. At this point, the switch will send everything to them thinking that that is the default gateway, and then that particular black hat hacker will send it down to the router, and it will keep a copy. So it basically becomes a man-in-the-middle attack. This is called ARP spoofing or ARP poisoning. There's ways to prevent this. One is by doing port security that we'll learn about down the road. So that's Ethernet, folks. Questions about Ethernet? Sharon,
I think I'm good.
Layer.
Actually, no, actually, this is probably something that I've been reading about and actually trying to learn at the same time. So, no, I think I'm good on the Ethernet.
Good. And I will say one of the important things to remember is that process of encapsulation and de-encapsulation. You know, the data gets encapsulated on the sending end, and then it gets de-encapsulated. Well, one of those steps is the layer 2 framing. And to be able to do that framing in Ethernet, you've got to know your MAC address. So you've got to do your ARP requests and your ARP replies. And so that's how it works. Okay. So we're going to move over. We got just a little bit of time to start chapter 6. Again, I'm not going to spend forever, but here is the process. Exchanging the data. We're going to take the data and we're going to start encapsulating it as it goes down through the different layers. Each side would get its headers placed onto it. There's the segments, there's the packets. Here's our frames and our bits, exactly what I showed you earlier. Again, reinforcing. On the other side, it gets picked up and then it gets, hey, is this my MAC address? If the answer is yes, it goes, is this my IP address? If the answer is yes, it goes up and says, okay, what is it supposed to go to? TCP, UDP, what is the upper layer protocol? And then it goes all the way up to the host. Well, it's important. You've got, all that's got to work, but you've also got to be able to get from the 192.168.32.11 network to the 36 network. Now these, folks, these are IPv4 addresses. You'll see they're in dotted decimal format, which means they're 4 octets, which means it's 4 sets of 8 bits separated by a dot. The octet is, I'll show you that in a minute, but each one of these can be between the value of 0 and 255, okay? So 192.168.32, assuming, and I'm going to assume a subnet mask of 255.255.255, if anybody watches this on the internet. That means that this is on 192.168.32 network, and this is on the 192.168.36 network. You've got to somehow, once you get all the way down here and get into the routers, you need a way to route this 32 network to the 36 network so it gets to the destination. This is going to all occur at the network layer, and it's going to be taken care of by the network layer and the routing processes of the network layer. So we're going to look in this particular chapter at different types of addressing at layer 3, IPv4 and IPv6. We're going to pay particular attention to IPv4, but IPv6 is actually looked at pretty in depth also, especially in the current CCNA. It'll be interesting to see in the new CCNA version 7 how much IPv6 is either stressed or maybe not quite as involved as what it is here. But here we have a transport layer PDU, which is the segment. It's got the segment header and the data. And then that comes down and there's going to be an IP header. And now I want you to think about this. At layer 2, we had a header that had a destination MAC address and a source MAC address. So what do you think is going to be in this IP header? Anybody? What do you think will be in the IP header? In the frame, one layer down below this, so down here at the frame layer, we had data, which would have been all of this dropped into here. And we had a header, and we had the dest MAC, dest, not best, dest MAC, and we had a SRC or source MAC. So what do you think is going to be in the IP header? At least has to be in the IP header. We're going to have a source IP address, and we're going to have a destination IP address. That's the only way we know how to get from point A to point B. So if we look back in the header of this communication, okay, let me take it all the way forward. 192.168.32.11 is the source IP, and the destination IP is 132.168.36.5. And so it's interesting and important for you to realize that devices can have both layer 2 headers, or information can have layer 2 headers, which is a physical address, the MAC address, and a layer 3 header, which is the IP address. And these are what are known as connectionless, so it's best effort. They are also media independent. It doesn't matter if it goes over copper, wireless, fiber optic, makes no difference. And also IP addresses or network layer addresses are what are called logical addresses. There's absolutely no reason why my IP in my office is what it is, 10.102.x. It's just that they decided this building was going to be 10.102.x. Very important concept. So IP is connectionless, which means you throw it in the mailbox and we hope it gets to the other side. Everybody goes, well, what in the world? How do we get connections from a web server back then? Well, that's handled by the next layer up. We're going to learn about TCP at layer 4, or at the transport layer, and you'll learn that at layer 4 you can have connection-oriented connections. But at layer 3, it's connectionless. So here we say sender doesn't know if the receiver is present, if it arrived, or if they can even read the packet. And the receiver doesn't know when it's coming. So at layer 3, it is connectionless when we're using IPv4 and IPv6. Again, best effort. They keep hammering this. So this is the third slide we've seen on it. So I think I would probably know the characteristics of IP and the fact that it's connectionless, best effort delivery, media independent. And again, here's another one. So not guaranteed, all these things here. You need to, again, make sure you're doing these things. Now here's the IPv4 header, and there's a great deal going on here. You're not going to be expected to know every single part of this, but you'll notice that there's a version number, which is 0100 to indicate it's IPv4. There's a header length. There's a DCSP, which is used, DSCP, I always say that wrong, DSCP, differentiated services, control point, diffserv, or code point, diffserv, and that's used a great with quality of service, okay? It's used also possibly for ECN, for explicit congestion notification. All the way down, we've got our protocol. Now this protocol is important because that's what it's being passed to above layer 3. So the protocol field is used to say whether it's going to be passed up to, if it's 1, it's passed up to ICMP, which is Internet Control Message Protocol. We'll talk more about that in a little bit. If it's TCP, it's going to be protocol 6. If it's UDP, it's protocol 17. Probably wouldn't be a bad idea to remember those 2 or those 3. Then we're down to our 32-bit, which, by the way, what are 8? 8 times 4 is 32. So if you say it's a 4 octets, it's 32 bits. So this is a 32-bit field for the source IP and a 32-bit field for the destination IP. And you'll notice they reverse these in the IP header versus the frame header because they assumed if the frame matched, then the device probably should be the correct device for to receive it. And so it will take in the entire header and then de-encapsulate the header and pass it up to the correct next layer protocol. Good example here, good header or a good activity too. I'm going to stop here and I want you to think about something. I want you to think about all that's going on in this process. As I go back and we look at the connection between these two and we say, okay, this host wants to pull you know, a web page off of this host, or this host is trying to serve a web page over to this host. Think about all the encapsulation, the need to put the layer 4 protocol information, the layer 3 source and destination IP, the layer 2 source and destination MAC addresses. Oh, I don't have the MAC address, so I've got to do an ARP request, got to do an ARP reply. I didn't even mention the fact that to know the IP address, we're probably going to do a DNS request up at layer 7. So all of these things going on. And then think about how fast we can do things on the internet. And it's really a miracle, because this information has to go through all these steps every single time you send information between 2 devices. And then kids today, I say again, I'm getting to be an old man. Kids today, they gripe when it takes 2 seconds for a web page to load. And I'm the same way, by the way. I get, if a web page takes more than 5 seconds to load, I'm done with it. But it's amazing what is going on in terms of all that's taking place in order to make this work. All right, are there any questions before I stop the recording?
No questions, but I will say this is very informative, and thank you for sharing this information.
Oh, you're very welcome. And I do hope, go and watch Kirby's items also, because I like to have my students watch multiple different lectures, even if they listen to me in class. It's not a bad thing to have your students go watch lectures out on the net. We actually have Dan Abrighetti of Dan's courses, who teaches for us in CyberOps. And so Dan has excellent lectures on CCNA also. So it's always good to get multiple different ways of looking at things. So I'm going to